CSIR-NEERI and Professor SEQUESTRATION. He did his PhD from Dr. H.S. Goyar Central University, Sagar, Madhya Pradesh in 1990. He did his diploma in environmental pollution and control from Institute of Rural Development and Research, Allahabad in 1994. He did his postdoctoral study from National Institute of Material Science, Tsukuba, Japan in 2002 with advanced material for energy and environmental application, including nanomaterials. He joined CSIR National Environmental Engineering Research Institute, Nagpur in 1994 as a scientist group 4-1. He has published more than 154 papers in international and national journals. He wrote more than 8 book chapters. He applied and granted more than 40 plus national and international patents. He guided more than 8 PhD students. His interested research area are energy and environmental material, including environmental catalyst, nanomaterial, adsorptions for various environmental application, air pollution control, heterogeneous catalyst and safe Taylor catalyst, cleaner energy generation, carbon capture, water treatment and management. So now I request to Dr. Nitin sir for delivering his expert talk on clean energy and emission control option for sustainable development. Dr. Nitin sir.
Well, good morning all, and thank you very much, Professor Shah, for the kind words. So I'll try to share my screen and please confirm if you can see the first slide. Okay, are you able to see my first slide?
Yes, sir.
Okay, thank you very much for the kind words. I think what I'm going to share today with you all, 2 or 3 things I would like to make some statements before I go for my lecture. That almost all of you are probably the faculty in engineering colleges, and I have a realization that in many things you definitely know more than me. Okay, so while introducing a topic, I'm doing that just for the benefit of those who are not much familiar with these areas. And please excuse me, because many of you must be having much better understanding, much better knowledge on these technical areas. Okay. So upfront, I apologize for that. Second thing, what we'll do, we have about 90 minutes, means maybe 80 minutes we'll take, and then we can have a couple of questions. So I have decided to, first deal with the cleaner energy. Okay, so what we'll do, we'll plan like this. We'll just see the energy scenario, the worldwide, what is the energy scenario, what is the scenario of greenhouse gas emissions. I have also prepared a couple of slides to show you the impact of COVID-19 pandemic on energy as well as emissions scenario. Okay, and then we'll quickly look into the cleaner energy options, and then finally I'll just share 1 or 2 activities of our group. Okay, one of the advantage of this platform, online platform, that we can make a lot of lectures and we don't have to travel. But the disadvantage of this is we are not able to attend the conference, although there is a possibility to attend, but we never get time, in fact. And that's a real problem, because we do not have eye contact. I do not know what have already been, explained to you, because if I had to physically come there, okay, or we had a physical conference, I would have come to know. But I have seen the program, and I have tried to structure or organize my presentation so that there won't be repetition. But as I was talking to Professor Shah, and I came to know that most of you, probably many of you, are from the mechanical engineering background, and I slightly changed my slides, and I'll be talking more on the automobile emission control from new and in-use vehicle. To be honest, I actually work in this area, and recently we are a part of a large project from Ministry of Environment and Forest related to the exploring some pilot studies for emission control from old vehicle. So this is how I planned it, and I'm going to show a lot of slides, and of course I'm going to give you a lot of stress, because I have also seen that after my talk there will be a talk on stress management. Okay, so please don't worry. And as I mentioned, that please enjoy this lecture and please feel completely free of discussing. Just 2 to 3 slides about my institute. Okay, what NEERI is all about. NEERI is a CSIR lab. Most of you must be aware about the CSIR. That is the largest scientific body in the country and one of the largest in the world. We have 38 labs. One of the lab is NEERI, which is dealing with almost all the aspects of environmental science and technology. And then we have dedicated departments like water technology, wastewater technology, okay, and considering the fact that energy has a lot of impact on environment, we have a dedicated division which I look after, is Energy and Resource Management Division. So in addition to the scientists, about 120, we have a very strong presence of students, which are our actually workforce, okay, and they are really the strength. We have done projects pan-India. Okay, we take advantage of 5 zonal lab of NEERI as well as other CSIR centers and CSIR labs. Okay, this is the group of the division I look after. It's called Energy and Resource Management Division, where I personally work actively on the diesel emission control, the after exhaust treatment technology, and I'm going to share with you some slides on this. Then we are working on another cleaner energy process, which is competitive technology to carbon capture. And I'm going to introduce this interesting work, because there is a lot of interest from the engineering community, especially the chemical engineers and the mechanical engineers. Okay, so this is the just a minute. Now it's okay. You are able to see the same slides in the presentation mode. Can somebody confirm?
Yes, sir.
Yes, sir.
Yes.
Okay, thank you. You can stop me if there is a problem in my audibility or the slides. Okay. So let's quickly see. Although somebody must have explained you the global energy review, I also prepared some slides to give you a background. In fact, okay. So those who are not from energy domain, and if they follow the newspaper, okay, nowadays newspaper write a lot about the energy as well as the pollution. Both the areas have become very, very important. But anybody who is not very familiar will get confused if we follow for say 15 days. While we are talking about the solar, and India is one of the most aggressive and impressive country when it comes to the solar and renewable growth. Okay. Suddenly you find a news that India's coal import is rising, in fact, okay? And of course, it's a very common news that our energy demand is increasing. The next day, you will see that we are making another impressive progress when it comes to the solar, okay, and the renewables. And very next day, then you will read something about the thermal power projects, that they are under stress. But very next day, again, you will see that our thermal power plant or coal dependency will be there. Okay, and of course, I need not tell you that there will be plenty of news about the global warming. So, if you just analyze for 15 days or maybe 1 month, okay, one thing is very clear to you, that it's becoming more and more complex. Okay, we'll try to understand what is the scenario now. Many of you, of course, you may be not as old as I am, in fact, and when I was a child or even 15 years ago, I remember that energy in India means providing electricity to rural home. If you ask even a scientist a question, what do you want to do in the energy? And the immediate answer or response will be, oh, come on, let us provide the energy to or electricity, not even energy, electricity to the villages, because there is a huge load shedding and there is a problem of, electricity. But today, energy also symbolizes, unfortunately, the pollution, the health impact, the climate change, the regional conflicts, all of you know, the country's economic jerk also. Suppose the crude oil prices goes up to $150 per barrel, there is economic jerk, okay? This strategic planning, they call it no more energy is just a requirement, okay? You need to plan it and it's a strategic sector. Without energy, you can't do anything, okay? And the renewables, the solar, okay? And we are now talking about 15 years ago, any kid will tell, okay, for energy, you need a fuel. Today, if I ask, what is this fuel for, say, windmill? What is the fuel for the solar, okay? What is the fuel for maybe geothermal? Then it's becoming more complicated. So it's evolving. That's the good part. It's evolving and there have been fantastic innovation in this. Okay. Now look at the growth and energy demand, and I have a reason to show you this, especially those who are not from the energy background. It is parallel to your lifestyle or your development or your mainly economic development. Okay. So this is the global GDP of regional contributor, and India, China are leading in fact in the recent years, so as many other developing economies. So GDP is increasing, our economic condition is increasing. Now, if you see the primary energy demand, okay, I will just switch these things. Yeah. What I want to show you that we are in say 2020. If you see the 1970 OECD, okay, the developed world, was dominating the energy requirement, energy demand, and energy consumption for that matter. And rest of the countries you can just see, okay, including China and India. It started gradually changing, and now we are at the 2020, where OECD is flattened, okay, their energy demand is flattened, which is something very, very good. China has made impressive growth from 1970 to 2020. India has also made pretty good, not as compared to China, okay, we have a lot to catch up, okay. And then the other countries are also progressing, okay. Other Asian countries also made very handsome growth. If you see the 2040, the growth of China will be still good, at least for next 10 years. India will probably be double, but still lesser than the China. This is how we are progressing, okay. Now, if you see the primary energy demand, and if you ask a kid and you show him this is the solar program for India and we are going with this, okay. Now, what is the distribution of energy demand sector-wise? One of the interesting thing is the building will use a lot of energy. What do we mean by building? Means the space where we call it, and air conditioning is going to capture a lot of energy. Okay, they are going to require a lot of energy in a country like India for air conditioning, and for the cold reason, of course, for the heating. Then the industry is a sign of growth, so industrial demand will also increase. This is an important slide for you. If I talk about the fuel, and from 1970 we come to 2000. In 2000, if you see the oil, this green is oil, then red is gas, and this is coal. So you can imagine almost close to 80 to 90% of the energy is coming from the fossil fuel. This was the scene in 1970 also. So not much improved. Now, if you see in the 2020, again this green, red, and this gray all put together is close to 80%. Okay, so despite the fact we want to work on the renewable, as of today, the situation is 75% to 80% we are using fossil fuel or carbon-based fuel. With the growth of solar so impressive in India and elsewhere in the world, and the renewables like bioenergy and other things are coming, I think you have a very interesting talk on solar thermal. Okay, we can expect it another 10 years, if not in the 10 years, 20 years, the scene will be completely changed and we'll have a very, very fantastic renewable option. As per this report from BP Energy Outlook, okay, if you see the scene at 2040, you can still see these three, okay, slots of fossil fuel is providing you 75% of energy, if not more. What does it mean? Why are we investing so much in the renewable when we have to use this big 70, 75%, 80%, unless there's some big innovation coming in next 10 years? The only reason is you can understand from your left side graph. Despite the very impressive growth in the renewables, your total energy demand or requirement is increasing so much that you will have no choice as of today but to also use the fossil fuel. Okay, unless there is some disruptive technology coming, okay, which I pray and I hope should come. Otherwise, as of now, the forecast is we are going to use about 60 to 70% of the energy by using fossil fuels. So this is what I wanted to highlight you. We need to be very, very practical. Now, if you see the primary energy consumption by fuel, it's more or less the same. The only thing is the left side graph is telling you a couple of things. If you see the x-axis, this is a 2017 scenario, evolving transition, more energy requirement. More energy requirement means we are going to use more energy from the fossil fuel sources. Less globalization and rapid transition. In case of rapid transition, you can see some change. Okay, they are going to use gas, but they are going to reduce at least the oil as well as the coal. Okay, if you see the CO2 emission, the best or most optimistic, ambitious, and we all should hope is this yellow one, where we call it a rapid transition. If there is a technological innovation, there are innovation in terms of the renewables and all these, the CO2 emission can be brought down, possibly. All right. Otherwise, this is a business as usual scenario. We'll have a lot of CO2 emissions. And if we have only energy demand, more energy, and we are not doing anything towards cleaning up these energy sources, we are going to land up in a serious problem when it comes to the CO2. Okay. This is the energy demand growth. So I'm not going to spend much time because everybody knows that India, China, Korea, and a couple of Southeast Asian countries are making impressive growth. Again, this is the same thing. CO2 is going to shoot because of the more consumption of fossil fuel, which is primarily due to the more energy requirement. And we need to do something to flatten this curve of CO2 concentration. This is India Energy Outlook. You can refer to this, this report, what India is planning. Quickly, impact of COVID-19 pandemic as we were expecting. If you see the historically, starting from 1900, okay, from 1900 to 2020, there have been some peaks where the primary energy demand was less. This was Spanish flu. All of us come to know about this Spanish flu through WhatsApp, that this is something happened about 100 years ago. Then Great Depression, economic depression. Then was the Second World War, where obviously all the industries were shut and all these things. Okay, so energy demand was less, up to minus 12%. There was another oil shock, second oil shock. Okay, not so much. And you can see here it is going down, in fact. And I'll show you a couple of slides that this has happened. So historically, last 120 years, this hasn't happened for more than 3-4 years. And my good optimism is that it should not happen for another 100 years. Okay, so this was a shock. So in China, the coal was down. Okay, renewables were up. But please mind, this is a percent contribution. So obviously, if the overall energy demand is less, we should first manage it with the renewables, okay, or the solar. And if not required, why to use coal? Why to use the oil? Every country made like that. Like in India also, coal was down, and percent of solar used. We can't change the production of solar. Okay, we can't change it overnight. So percent contribution of solar was high. This is global generation, how it affected. Obviously, the trend was same. Coal was down, solar was up during this period. Okay. This is the growth of 2018 to 20 for solar PV. Progress was fantastic in 2018, but it's again a percent share. Okay, so we are still making very, very good progress, in fact. So right now you can see the oil demand was down close to 9%, and total energy demand was more than 6% reduced because of the industrial down. So as this CO2 emissions, sometimes there are debates. Like some people say, not all the CO2 emissions are coming from anthropogenic sources or from energy or for transport. That's true. There are a lot of natural sources, but you need to believe that majority of the CO2 and CO2 problem as a global warming is because of anthropogenic sources. And this COVID pandemic or Corona pandemic was a wonderful validation of those things. Okay, this is the CO2 emission. Those were already down during the pandemic. Okay. It was as much as about 16% reduction in the CO2 during the lockdown. There was a worldwide lockdown. Some countries had a longer lockdown. Okay, and not only CO2, SOx and NOx were also reduced because the combustion or the energy is one of the major sources of these emissions. These emissions, obviously, once the lockdown was relaxed, started increasing. So this is a very good validation that anthropogenic sources also contribute. For those, I strongly believe. Of course, there are hundreds of ways to validate this data, but this was a validation, all right? So CO2 emissions are now again back to their normal. So obviously we haven't seen any concentration change in the CO2 because it takes years. And there's a, like a paper also, the carbon emissions for 20 come down by 8% due to lockdown, okay? But all these are very temporary phenomena. Nature, which is one of the most reputed science magazine, they also confirm there was a temporary reduction in daily global CO2 emission, not in the concentration, because the concentration is a cumulative over the years and decades, in fact. Okay, so this was the background. Now I'll take you to some of the things related to cleaner energy, what we are also doing. Mostly at NEERI, although we are working on hydrogen generation through photocatalytic water splitting, there is a group with materials division. I was also part of that group. There are people working on the hydrogen storage. There are people working on waste to energy. Okay. Otherwise, most of the things we are doing is, like the post-treatment of anything or after exhaust treatment. So my focus will be mostly on that. This slide I'm repeating for a simple reason that we know the CO2 emissions are primarily from the fossil fuel or energy sources based on the fossil fuel. There are two ways to do that. One is stop using or start using or minimizing the use of, these fossil fuel. Second possibility, as of today, the projection says that we are going to increase our fossil fuel consumption. While we should ideally reduce, we are going to increase. Okay. So what are the options now? One option is ruled out, that we are going to replace this fossil fuel totally with the renewables or sustainable or the green. Okay. We are going to increase the production of renewables, but we are not unfortunately able to replace it because of the very, very high demand in the future. Okay. Second option is making energy technology cleaner or sustainable. Okay. How to do that? For example, in India we have a lot of coal. Okay, and at the end of the day, it will matter about two things: techno-economic viability. So in techno-economic viability, economic is also very, very important part of that word. Okay, so you need to now understand that what will be commercially viable, economically viable will be a priority. So coal is plenty in India. Unfortunately, coal is not so clean. So one of the best options for us will be the clean coal technology. And then of course, nuclear and hydro and other renewables will be there. Okay. So the background of these slides is fossil fuel consumption is likely to increase at least for next 2-3 days. Practically no assimilative capacity left for air pollution as well as CO2. Okay. So these are very contradictory. That fossil fuel consumption is increasing, but we don't have any space for pollution. Okay, there's no limit available for pollution. So we need to make these options, this fossil fuel, much cleaner. That is one of the strong policy, okay, strong option rather. Second thing, we need to also understand the indirect impact through the life cycle assessment. Okay, I'm a strong believer that for everything, practically for every resource, for every product, for every energy option, we should do the LCA or the life cycle assessment. Now, when it comes to the environmental pollution related to energy or the fuels, there are two fundamental issues. One is a global issue of CO2 emission, which has a global impact in terms of the global warming, the climate change and all that. Second is a more localized issue, although these are also having a global impact, like water pollution, soil pollution and the air pollution in terms of conventional pollutants like NOx and the sulfur dioxides and all that thing. Okay. Let's quickly see the CO2 or GHG emissions. So as I was mentioning, there is no assimilative capacity left. All of you are quite aware of the right from Kyoto Protocol to the Paris Accord. Okay, and there's something like 2-degree change. If the change in the climate or global warming is more than 2 degrees Celsius, it can have a catastrophic impact. It can impact almost all the sectors. We need to understand. Okay. And there are hundreds and thousands of evidences we all see, we all read every day. So we are not going to go into the details. Some other opportunity I'll explain you if you are interested. What are the applications? Okay. So half degree means heat wave duration, rainstorm intensity, sea level rise, and biodiversity losses. Okay. So we need to control it. Okay. There are evidences. I think this was clear that even 2019 was second or third warmest year on record. So there are scientific evidences to believe. Now, just 4 or 5 slides I have specially introduced, which are not for you, but probably you can that way convince your students and encourage your students to understand what is the direct emission and what is indirect emission. Okay. So direct emission, we all understand we are burning coal to generate electricity, which is coming to our home, which we are using for air conditioning, for electricity, and for everything. What are the indirect emissions for that matter? Just take an example that I do cycling every day, say 50 kilometers, okay, just as a hobby and to keep myself fit. If I am replacing cycle with my motorbike or car, I'm doing a fantastic job, okay. But if I'm eating too much and then using cycle to burn my calories, come on, I'm not doing any good job. Because after consuming the calories, if I use banana, I will sort of release this much of CO2. If I'm using cereals and milk, 90 gram, okay, for a mile, just 1.5 kilometer, 1.6 kilometer. If I'm using non-veg, then for a mile I'm releasing 200 gram of CO2, which is almost equivalent to a car. Okay, powered by cheeseburger, more than a car. Okay, so instead of eating too much and cycling, I should better use a car. It's just relative. I'm just kidding. So this is the way we should understand the indirect emissions of carbon footprint. Okay, so carbon footprint is a very, very important thing. You need to sensitize your students that there is a direct emission. We understand the power generation, even those from the, any background, the chemical engineering, chemistry, or even mechanical engineering. We understand what is the efficiency of our power plant. Okay, so we can easily calculate that this much of megawatt of energy we consumed or we generated, how much of coal we have used. Okay, and coal is C plus O2, we can calculate CO2. That's very easy. But what is important is indirect emission. We all understand what is the transmission losses, what is the energy we have spent in mining of coal, transportation of coal from the mine to the power plant. What is the energy required while producing these machines we are using in the power plant? Then the transmission lines, okay, fine. So built emissions, okay, or built footprint is very, very important concept. I often ask the student that what is the carbon footprint of solar energy, and they obviously respond 0. It cannot be 0 because you have already invested a lot of energy to produce the solar panel. It's a high temperature process. Okay, so that is overall we should see what is the carbon footprint of energy, any energy option, and for that matter any process or any product. It is very, very important to sensitize or even like work out the carbon footprint. For example, for this kind of a shirt, it takes about 2,700 liters of water, okay, and a huge amount of energy as well. So you can imagine the footprint of a shirt, and everybody is doing that. For a car, we understand the CO2 is coming from the exhaust pipe or the tailpipe because we are burning the hydrocarbon-based fuel or carbon-based fuel. But have you ever thought of the CO2 emissions which have been emitted during the production of a car? So if a car is met with an accident after 6 months, okay, you lose so much of CO2 emission which went out, okay, which were released while producing the car. Okay, so that's the manufacturing footprint of car. Similarly, you can explain to the students that when we are using LPG, it is not only the LPG we are burning and then it is releasing the CO2 emission. We should calculate right from the extraction of crude oil, transportation of crude oil from Saudi Arabia to India, then the refinery, we are processing, we are emitting a lot of CO2, okay? And then we are producing LPG, and then LPG is transported by obviously the railways from that refinery to my place, like I am in Nagpur. And then it goes to the bottling plant, again energy consumption. Then from bottling plant, it is going to my dealer, again by using a diesel vehicle. From there, again, he uses a smaller vehicle, bring it to my apartment. In an apartment, he is using my elevator or lift. So this is the indirect footprint, which is a huge, okay, and which is very much available. Fine. Just one last example that what is the big advantage of this online platform? Okay, why? It is typically 3 ton per scientist is estimated CO2 emissions, if you are using international conferences and flying with the aircraft and using other things. All right. So these calculations you will find on internet. It's very, very interesting. Okay. So of course, it is very important to meet once in a while, but we should always think that it is not that I have just traveled, so I have consumed on the aircraft or all these things. It's very, very high footprint for each and everything. So we need to look into the carbon footprint of all resources we consume, all energy options. We also need to look into the carbon footprint of final energy delivery, of final application under the actual condition of its use. Okay. What is LCA? From cradle to grave? Okay. Right from cradle to grave, we need to calculate everything. Okay, what is the carbon footprint? What is the material footprint? What is the energy footprint? Only then we can compare it. Now, I will strongly suggest, many of you might be expert in the LCA, but this is one thing we should promote. We should train our student, and we should also take them. Okay, because this is also very contextual. Okay, so don't look into any other option in the isolation. It's time to subject practically everything to the life cycle assessment, even environmental process. I need to clean a lake. I'm preparing some material. Okay, I'll just go clean the lake and come back. But I need to find out what material I have used, how much of energy I have consumed. How do I dispose that material which was used in the lake and now it is loaded with the pollutant? Okay, so everything from cradle to grave, I need to find out, and I should do the LCA. And why I'm saying it should be done in a local context, because those who are familiar with LCA, they're using a lot of databases, a lot of software. Sometimes, if you are not properly following some process in environmental point of view, for example, transportation of coal, so you can see that the transportation of coal from the mine to the power plant doesn't have much significant footprint, environmental footprint. But if you are not doing it properly, where I have found, and in India, you can see it, in fact, if you are transporting poorly in a truck, which is not properly covered, there could be a lot of emissions. So it should be done contextual, okay? So we usually don't do that, so we should be doing that. Now, let us talk about the control part. This is like the background, what is the direct emissions and what are the indirect emissions. And if you want to, contribute, or if you want to understand the indirect emission, I'm sure the LCA is the best way to do that. Okay, so now prevention is better than cure. So first we will see the preventive things. Okay, and then we will see the control options. Okay, so prevention, one of the things, one of the buzzword, if you ask me, I'll go by the efficiency. Okay, I'll simply say, efficiency is something very, very, very important. And all of you understand. Let us see that we are talking too much about that CO2 emissions are from the energy. Okay, whatever CO2 emission, whatever global warming is there, it is mainly because of the energy, and because we are using a lot of fossil fuel, carbon-based fuel, we are burning it, and that's how CO2 is producing. So reducing the energy demand, okay, and we can take care. If you see these slides, I borrowed from Dr. Sonde, who is one of the best energy experts in the country. Okay, so if you see the power generation, this is the typical efficiency. What does it mean? What do you mean by efficiency? If you see the subcritical, or if you see the genset, it is anything between 12 to 38%. Say average 25%, we can take it. What does it mean? As compared to the theoretical energy available, okay, the CV value is available, we are able to extract only 25% of the energy for actual use from the theoretical energy. Okay, supercritical, which is ambitious, 40 to 45%. Okay, and GT combined cycle, we all wish it should come 50%. So as of today, we are losing almost 70% energy during the production. For 1 megawatt, this many tons of coal is required. You require more or less 3 times coal, because you are losing a lot of energy there. Okay, then transmission and distribution losses, we understand about 15-20%. Okay, so from, say, if you see the Rankine cycle, from fuel extraction island, okay, of course there is energy involvement everywhere. Then the combustion island, the power island, transmission island, and the distribution island, almost 80% is gone, more than 80%. According to his calculations, more than 80%. Okay. There are opportunities for innovation. We should also take it positively. As a mechanical engineer, if you make a difference, we all know we all understand the theoretical limitations. We all understand the thermodynamic limitation, but we are not talking about the 30% improvement in the combustion efficiency. Even if you make a 3 to 4 or 5% of difference, it's very, very significant. Let's move to the demand side. Okay, the demand side is compressor, about 25% of even the 5-star compressor might give you 30%, a little more. Illumination, they have been a very good innovation, quite disruptive. Okay, with the CFL, and they have been very good programs also. So that's our hope. When we can make it in the illumination, which was not sort of imaginable 10 years ago. Okay, now we are talking about 70%, 75%, 80% of efficiency. Let us try for other things also. Automobile, maybe 30%, furnaces, 30, 50%, 40%, depending on the furnaces. Air conditioner in this range. Cooking stove from 12% to say about 40%. So what does it mean? We have seen the production, energy generation, and we have seen the energy use. All put together, close to 80% or 85% of energy is being wasted. Means whatever CO2 is going there, theoretically, hardly 15% of the CO2 should be released in the atmosphere. This 85% is only because of the efficiency and other losses. Okay, so we know that we cannot improve to 80%, but while taking from 10-15% to say 20% will be a big deal, very, very big deal in fact. So that's why they say that energy saved is the cleanest form of energy generated. Okay, and that should be the mantra. But fortunately, the Bureau of Energy Efficiency in Government of India has a very impressive, aggressive plan. And among my group at CSIR, we are working quite actively in this. There is a subgroup, we call it an Energy Efficiency and Management Group, and at least 7-8 CSI lab put together is taking up this program in a big way. And next 5 years, we want our prominent presence in the area of energy audit, including the energy audit, industrial energy audit. So this is what I wanted to tell you. One or two things. Sometimes, if you are interested, and suddenly you might, get confused. That if you see this graph which is coming down, which is always very, very good from 2000 to 2013. What is this saying? CO2 emissions GDP ratio. Okay, so from this graph, it looks like that the CO2 emissions are down like anything. Okay, but we need to understand this is as a function of your GDP. Okay, so I don't want to confuse you more, but we need to be careful while seeing these kind of figures that okay, it looks like CO2 is going down. No, you should see the CO2 emission in absolute value. These are all the options, good option rather, to clean your economy, basically. Okay, today your GDP is this much, say 10 unit, but your CO2 emissions are high. We know that your GDP is going to increase to 50. Okay, so your CO2 emission will also jump by 5%. You should control it. This is a good strategy. But tell me one thing: if you are increasing your population, number one, if you are increasing your GDP, number two, okay, you are bound to increase the CO2 emissions. So these are quite, I would say, debatable issues. Okay, so there are things like carbon intensity and all these things. So you may be able to control your or reduce your carbon intensity, but if you are increasing your demand, if you are increasing your population, resources, and everything, okay, in absolute term, you are going to increase more CO2. And as I mentioned to you, there is hardly any assimilated capacity left. Okay, so we'll just see that. We understood that there will be increase in the energy demand for next several decades. Point number one. To meet this increasing demand, although world is working on renewable and green energy technologies, unfortunately, we cannot meet the entire demand. So the option left is we are continue to use the fossil fuel. So one of the most important and more critical or equally critical to that parallel to like renewable option is to clean our fossil fuel based energy option or carbon based energy option. So a part of that is of course the energy efficiency. The another part is carbon capture, utilization, and sequestration. Why? Because you are bound to use fuel, carbon based fuel, which is going to emit the carbon dioxide. How to control it? So we'll try to control it, one thing, or let us try to use it. What do I mean by use it? Those from this area can easily follow it: carbon capture, utilization, and sequestration. So traditionally, the CO2 is also called carbon. So we call it a carbon capture instead of CO2 capture. Here you can follow. There's a power plant, okay, or any industrial plant, a captive power plant, which is using the carbon-based fuel. It is generating CO2. Now CO2 is released. The first thing is to minimize the CO2 release. The second thing is, okay, you are done efficiency, you're done with everything. Now this CO2 is released in the atmosphere. So before it is released in the atmosphere, let us try to capture it. Okay, so there are adsorption and absorption processes through which you can capture the CO2, okay, and a clean air is released. Fine. Then the CO2 can be converted into bicarbonate or the carbonate, and it can be used. Then best thing will be probably to use this CO2 to convert into a fuel, because it is all produced from the fuel. Then there are other possibilities to utilization of this CO2. One basic question is, why don't you simply convert this flue gas into some product? Okay. The problem is the CO2 concentration is around 12 to 15%. And in any chemical process, you need quite a pure CO2, like 95% plus. Okay. Why this is diluted exhaust? Because you are using air for the combustion of coal. And air contains 78% to nitrogen. So the exhaust composition is something like 12 to 15% CO2, little bit of oxygen plus nitrogen. So you need to pre-concentrate it. You need to capture this CO2 from 12% to say 95%. Okay, that is called carbon capture. And then U stands for utilization. You can convert this CO2 to some useful product. And sequestration is, I'll explain you about the geological sequestration. So here comes again another possibility. From power plant, you release the CO2, we have captured it, we have used some processes like electrolysis, we convert it into carbon nanotubes, okay, and there's a big market for the carbon nanotubes. But I don't think so there is such a huge market as of today that we can take care of millions of tons of CO2. So you need multiple options to convert into multiple products, all right. Now come to the sequestration part. There is a good possibility that you can capture the CO2 and you can sequester or store it geologically. Okay, so there's a possibility that we can store it inside the porous rocks. Okay, there are like empty spaces from where we extract the oil, and there we can probably store the CO2. Okay, so it can be pumped to extract the oil, and we can replace the CO2 with the oil. So this will be trapped there. There are some environmental consequences of this. Okay, so first we need to capture it, pre-concentrate it, and then use it. Now, if you don't want to use it and you want a geological sequestration, then why do you want to pre-concentrate it? You may not. Okay, but the reason is you need to pre-concentrate it. If you are producing at X place and you want a geological sequestration site at Y place, and the distance is 1,000 kilometers or 500 or 100 kilometers, then you need to transport CO2 from power plant to this geosequestration site. And transportation means consumption of fuel. Consumption of fuel means you are also releasing the CO2. So you might land up in releasing more CO2 than sequestering. All right. So it is better to capture, make it pre-concentrated, and then you transport it. Okay, instead of transporting nitrogen along with. So all these things become feasible when there is a less energy penalty, there is a less cost involved, and most importantly, by doing anything like this, you should not release more CO2. You should be very, very careful on that. Okay. Now, this is a conceptual thing that you release CO2 by combustion process, by using fuel for generating energy. So the best will be if we can transform this CO2 into fuel back. Say methanol or ethanol or anything, if you can do it for the gasoline in future or any fuel. But you should keep in mind, while converting this CO2 into fuel, back into the fuel, you should not invest too much of energy. And you should use, say, renewable energy, something like solar. Otherwise, you will end up in emitting so much of CO2 back. Okay, so this is ideal. For example, you take CO2, you activate using some kind of a solar energy, make some reactions again using the solar energy and convert it into a fuel, liquid fuel. Okay, so the carbon capture and sequestration market will be very significant in future, and there's a lot of grants, a lot of R&D efforts are being made. Okay, and why we understand that we are going to use the fossil fuel, we are going to emit a lot of CO2, and CO2 there is hardly any accelerated capacity. So the R&D related to CO2 capture, sequestration as well as utilization will have a lot of importance. Okay. Here I would like to show just in 5 to 6 slides what we are doing in this respect. There is an interesting process we are exploring, which is known as a chemical looping combustion. Okay, this is a competitive technology to carbon capture. Okay, I hope you are able to follow me that from a power plant there is an exhaust stream in which 15% of CO2 is available. We need to make some absorption or some kind of a process to concentrate it from 15% to 95%, and we need to take off the nitrogen available. Now, I'll give you one reaction which many of you might be familiar as well. In a combustion process, suppose you are using coal or you are using methane. Instead of air, if we use pure oxygen, what will be your reaction? Coal is C, oxygen is O2, C plus O2, CO2. So if I am burning coal in pure oxygen, I will get pure CO2. Okay, not diluted CO2. What does it mean? I need not to go for the carbon capture. I need not to go for the separation of CO2 from and pre-concentration of CO2 from 15% to say 95%. I can use it. It is known as oxy-fuel combustion. So instead of air, I am using oxygen. But the problem is, can you afford to produce so much of oxygen for the power plant? And how expensive will that be? Okay, so oxy-fuel combustion is not feasible economically. So there is a possibility we can use the metal oxides. Okay, there's a little bit of chemistry. I'm not going to go in the details because many of you are having a mechanical engineering background. So we can use metal oxide like nickel oxide, and we can introduce fuel like methane. So this methane will react with nickel oxide. Okay, here it will produce CO2 and H2O. Okay, and nickel oxide will be reduced to nickel, and this nickel is either transported to another reactor, or once nickel oxide is reduced to nickel, you can introduce air instead of fuel. What air will do? It will reoxidize nickel metal into nickel oxide. Okay, and it forms a loop. So this second reaction of nickel metal to nickel oxide is very, very exothermic, and actual energy comes from that reaction, not from the fuel reaction. Okay, so there are some systems, some pilot plants. One, I think, Technical University of Vienna has seen one pilot plant, which is one of the best pilot plant. Okay, so the key to this development is oxygen carrier, nickel oxide or copper oxide. Copper oxide is also very, very good, but unfortunately, the reaction is feasible at about 800-850 degrees Celsius, and these metal becomes soft. So you're talking about the fluidized bed. So once the metal particles become soft, they will form a lump. It cannot be used. So at our group, these are some of the standard metal oxide couple which are used for chemical looping combustion. Okay, and this is like theoretical potential. We calculate what compound we are using. It's for the first time our group and a Swedish group tried together that instead of single oxide, we should try a combined oxide or mixed oxide. So we tried copper Mn base oxide. This is the theoretical value of oxygen. Okay, this is mixed oxide. And then we synthesize this material. We use them for the, we have some laboratory evaluation setup. This is very, very useful fixed bed reactor where we can use a mass flow controller, okay, and you can prepare any kind of exhaust gas, whether this was a vehicle or the power plant or anything, okay, and this is the reactor, we can use it. Then you need to do the reaction and try to find out how much of oxygen it's providing. This should be used for hundreds of cycles, but in the laboratory we cannot use it, okay. So we need to do that for at least 10 cycles, okay, and then we should establish that this is one of the good material or potential material. So we have done this experiment. Now we are looking for some collaboration of mechanical engineering or chemical engineering group who are good at like the modeling as well as the bench scale studies on fluidized bed. Okay, so because this needs to produce a couple of kgs, and then we need to work on the fluidized bed whether this material is good. Okay, so now I am more or less sort of completing first part of my talk, which was related to energy, before we switch over to the automobile. So I wanted these two separation, otherwise there will be a lot of confusion. Okay, so as regards to the energy related thing, okay, we will just conclude here, and then I switch over to the automobile part, and that I want you all to look quite independently or separately. And where being a mechanical engineer, probably you will enjoy more in that part. So as far as energy, cleaner energy issues are concerned, again to repeat, the energy demand is rapidly increasing. Okay, and because of that rapidly increasing demand, our renewable development or renewable growth, okay, or production of renewable energy is not able to match that demand, because it takes time, it takes investment, it takes innovation and R&D, okay, and installation also. So because of that, we are likely to use fossil or carbon-based fuels for decades to come, for sure, until 2040 and 2050. Okay, this means, first of all, several energy options and improved energy efficiency will be very, very important. Promoting a single option can be risky. So you should always take it, somebody is coming and giving you a talk on, say, hydrogen or methanol or the solar. So naturally, they need to highlight what is good about the solar. And ideally speaking, yes, if you can afford to completely replace it with the fossil fuel, there is nothing wrong. Okay, but as of now, we need to understand for next 10 years, if not for 20, 30, 40 years, we will have an energy mix. Okay, so we need to have the several energy options and improve energy efficiency option, which will be very critical. Whatever you want to use solar, you want to use anything, you want to use biofuel, there will be some footprint. There will always be some environmental footprint. Okay, so wasting energy is the worst thing. So you must practice energy efficiency irrespective of whatever you are doing for the energy generation. Okay, so promoting a single option can be risky. Okay, it cannot be done in fact. Then CCUS, carbon capture, utilization and sequestration will be very critical. Why? Because we are going to use fossil fuel. So we need to work on that. So as the coal gasification and clean coal technology or clean fossil fuel based technologies, we need to work on that. Life cycle assessment is very important, and that too in Indian context. Okay, we need to work out that how it is impacting when we are using our own coal in a usual way, in a clean way. Okay, and how much we need to invest if we are importing some technology and all these things. So we need to really do the life cycle assessment, and there are wonderful studies being done on the LCA of different energy options. Efficiency will be one of the keys for sustainable development. I'm very, very convinced we cannot afford to waste any resource. I'm sure you all must be aware that if you throw 1 cup of coffee, it feels that we have thrown maybe 100 ml of water. Okay, but the water footprint of 1 cup of coffee is estimated from, I think, 30 liter to 100 liter. Okay, so that much of water you are wasting, because we just think the volume of coffee is 100 ml, so how come it will be in the liters? Okay, so you should calculate when the tea or the coffee plants are going, we need a lot of water to feed them. Okay, and then there is a processing of coffee and everything. So there's a very, very huge carbon footprint and water footprint for every resource we use. Okay, so we must be very sensitive to that. Then we should have policy issues, because we need to try the holistic approach. Okay, nowadays we are talking about the decentralized energy system, which is a good idea, because the central grid is fine, the mega grid is very good, but then there are the transmission losses. Okay, so if you can have now there is a concept of energy island. Okay, energy island means you have a town, okay, of say 10,000 or 20,000 people. I know the demand of that town of energy demand. I will see what is the location, if it is a coastal area, what kind of area, what is the potential for wind, what is the solar energy potential, okay, and then I'll have the multiple option of energy generation. And then one of the very critical thing nowadays is coming up, and very good tools are coming for that, is an integration tool. So those integration tools are very important to decide which energy vector or generation vector you should try, what kind of energy demand is there, and what will be the best option for you. Okay, so these are the very good R&D opportunities for all of you. I am a material scientist, so I have a limitation, but I collaborate with many people, in fact. So one good thing is it's an interdisciplinary area of research which is becoming even more important nowadays. Okay, and second thing is a collaborative efforts. Okay, between academic research institute. Sometimes I feel universities are the best placed, and in foreign countries you'll see the university has such strong R&D setup. Because there is a physics department, there is a chemical engineering department, there is a mechanical engineering department, so is engineering colleges. So there should be very, very strong collaboration. Okay, so I'll quickly switch to another presentation. So just hold on for a minute, or if you want, you can just take a break of 1 minute. So can somebody confirm, are you able to see my new screen?
Yes, sir.
Fine. So just give me 1 minute and I'll just join you. So I think we are left with about half an hour, I would say. So maybe 20 minutes, 25 minutes, and then we can take some questions and discussions. So I'll take this opportunity because I'm actively working on the automobile emission control. All right. So again, the after exhaust treatment. I don't work on the engine and these things. I rather strongly collaborate with the other people. So in automobile, also the situation is quite same. Okay. If you see the projection on your left side, which is slightly old, in fact, 5 years ago, this is a global fleet increase and diversifies. Okay. Here also, this figure has slightly changed. Okay, this figure has slightly changed, but the message is that if you are expecting, and there have been a lot of like claims and counter claims and media news and whatnot, actually, that probably by 2025 we'll completely ban the IC engines, or by 2035 it will be difficult to see the IC engines, or by 2050, okay, it will be all in the museum. Okay, but the scene is like, as of now, I wish it should happen, but it will not happen. As of today, it is highly unlikely that we can completely replace the fossil fuel or the IC engines with the e-mobility or hydrogen or methanol or anything. Okay, I wish that their contribution should be very, very high. That's the best situation. These are some of the prediction in which 2040 also we are likely to use a lot of vehicle which will be IC engine based and based on the fossil fuel. Okay, and this is like your automobile population growth. Okay, so those are the fundamental problems, actually, to be honest. These are like statistics and related to the share of oil consumption as well as the transportation, because the oil consumption, a significant part of the oil consumption is for your transportation need. Okay, so that way the transportation's share to energy consumption, and especially to the fossil fuel based energy consumption, is very, very high. Okay, at the same time, the transport is a major source of PM 2.5 or the smoke or particulate matter emission control emissions. We know the NOx emissions, non-methane VOCs, and also the CO emissions. Okay, so these are the distribution I'm not going to go in the details because whatever you want, you can just, at the click of mouse, you can find it from different sources of CPCB or international sources or whatever energy statistics I have shown you. That is mostly from BP Energy Outlook, okay, which is petroleum, or IEA, International Energy Agency. And this data is from CPCB, very good databases they have. Now, again, I want to share with you, many of you might be aware of this, but whenever you get opportunity to talk to the people and some, like students or policymakers or anybody, okay, you know the Euro 6, we'll come to that. It's one of the cleanest engine in the world. You know how the automobile industry has made progress in last, say, even 20 years for that matter. You got a fantastically clean engine, okay, you got a fantastic fuel. But still the automobile emissions are increasing. There has to be some reason. One very clear reason is the number of automobiles are increasing. Okay. But second is we need to understand that what is the fundamental of any intervention to control the automobile emissions. One is we need to reduce the vehicle kilometers per passenger. What does it mean? Why do you need to travel so much? If you go to the Bombay, the whole Bombay is traveling in the morning and again back in the evening. Okay. What is the need? That shows you are poor, and sometimes I call it a horrible town planning. Okay, you have planned your town in such a way that everybody has to move from one place to another. I often quote one example when I did postdoc in Japan. So I went to the city office with my counselor because language is a barrier, and I asked that I want to get admission of my daughter in a decent school. And the cross question was, "Are you coming from India?" And I feel a little offended. Why are you asking like that? So every Indian asks this question, okay? So where are you staying? I told in this area in the international house. Then he said, "Sir, just don't worry. You are staying in the Ninomia area. Please show your city office card, okay, to the kindergarten, which is close, which is in your area. And by the way, you cannot take admission in any other school, number one. So you have to go there and show your card and you will be admitted in that school. Number two, all the schools are exactly same. They get same education, they get the same food, so you need not to worry, okay? So my problem is solved. And what in turns the country has gained, the travel related to schooling has minimized. Because she used to walk, I used to go at the most by bicycle or walking, okay? While in India, you can see right in the morning from 6 o'clock to 9 o'clock, it is all the vehicles are traveling or going at the full speed, carrying, okay, or ferrying students as well as for those who are going to the coaching classes. So this is one of the examples. So this is how we should reduce the kilometers per passenger. Second, reduce fuel per vehicle kilometer. What does it mean? Improve the efficiency, which is being done. Now you have a very good vehicle, but the reason is what? I'm sorry, not the pollution. The reason is you save your money. Okay, so that's why it is becoming an environment-friendly vehicle. Okay, but then there are SUVs which are having a very poor efficiency. Reduce fuel per passenger kilometer. Suppose you need to, of course, travel minimum. Okay, bare minimum you should travel. You have to go for shopping. You have to go for the recreation. This suggests you the mass transportation. If you are using a car, one passenger, the fuel per passenger will be highest. If you are 4 people in a car, obviously the fuel per passenger will get divided by 4. If you are using mass transportation, it will be less. Less fuel means less emissions. Reduce pollution per unit of fuel means produce a clean engine or put something like catalytic converter so that it becomes clean. Reduce cost of per unit emission control. All right, you need to try something indigenous. Okay, and then you can do that. Just give me a second. Where is the other school? So we need to reduce the cost, otherwise people will not be able to afford it and will lose it. Fine. So one more thing I would like to highlight here: control of emissions from new vehicle should not be the only aim of automobile emission control in India. Now you have a Euro 6, okay? So it's not that when you come to Euro 7 or Euro 8, that's the thing. Now, how to reduce the pollution from automobile? One is the advanced engine. We are touching the limit. Very, very good progress have been made, and thanks to automobile companies or engine companies or engine researchers, this has been done. Improve the fuel quality. This has been achieved. There are some problems related to adulteration, but that is very minimal. Okay. So now you have a Euro 6 grade fuel in India, which is less than 10 ppm of sulfur. So very good quality fuel is there. Driving behavior improvement on road conditions. This contributes a lot. Road dust, I'm sure you know, and if you do not know, road dust is one of the major contributor of particulate emission. It is not only the diesel emission, road dust also, because of the poor road conditions, right? And driving behavior, you know, like we call it in India, that every Indian has his own driving cycle, the way they drive, okay? Then comes, you know, like the traffic congestion is also one of the very big issue. Then improve tailpipe emission by implementing standards step by step and using the after exhaust treatment. So I must say that India has been doing it in a very, very impressive way, starting in the early 90s when catalytic converter was introduced. Now we are at the Euro 6. And again, compliment to the automobile industry and all those who are involved in that. Transportation and traffic management, very poor. Average speed in Bangalore and Delhi, I think, is less than 10 kilometers per hour. So obviously it will be more polluting vehicle, and your vehicles are not designed to run at that speed, okay, 10 kilometer or less than 10 kilometer per hour. That's your average speed. Reduce emission exposure. Okay, this is, you can quickly understand why people debate about the e-vehicle and the IC engine vehicle. So there is a debate, or there is a, not debate, an argument that if you are producing electricity from coal and providing into e-vehicle, what is the advantage? One advantage in this case, of course, since you are producing the electricity from coal, the CO2 emissions will be there, okay? You are still using the fossil fuel. But the difference is, if you are producing electricity in one power plant, say in Delhi, and you are supplying that electricity to 30 lakhs vehicle, okay? And in the power plant, you have got a 3 stacks or 3 chimneys or 4 stacks. It is easy to control emissions from those 4 decks rather than 40 lakhs vehicle, okay? And these emissions from the vehicle will be in your exposure zone. Those will be released very close to your office, very close to your house, okay? So you have a more exposure. So that's the advantage of this. Inspection or maintenance, all these things red I am intentionally putting because these are the weak areas, especially in India. Inspection and maintenance of vehicle needs to take up in a very, very strict way, okay? And control of emission from old or in-use vehicle is also a big job to do, okay? So these are the major efforts for cleaner passenger and heavy-duty vehicle in India. Decarbonizing fleet, okay, now we have a CAFE regulations and everything. Improved fuel efficiency, I already told you, okay? Reducing overall environmental footprint is an issue, but which is also taken up. Now the industry is very sensitive about the carbon footprint and overall environmental footprint. But I think end of pipe or disposal of vehicle is still a problem in India. All right. We'll quickly see what kind of technologies are being used for diesel emission control, because diesel has been in limelight. That they are the most polluting vehicle, and you must have heard that many major automobile companies have stopped producing or reduced the production of diesel vehicle, and they are switching to natural gas and the gasoline. Okay. So diesel, you know, like the major problem with the diesel vehicle is a particulate matter, or we call it a smoke. Why smoke is black and why the emissions from the petrol vehicle is not so black? Because there are these particles, black particles, okay? So if you see the particles which are coming out of an engine manifold, okay, and they are now traveling in the exhaust system. So there are two phenomena happens when they travel from manifold to the tailpipe, okay? One is good and one is bad. What is good? These are very, very tiny particles here when it is released from the engine, okay? So they start colliding with each other and they get agglomerated. So bigger the size, less harmful, because it is not penetrating to your lungs, okay? Your respiratory system or nasal system will trap it. That is the advantage. What is bad? Unfortunately, there will be some gases or these hydrocarbons which will get colder, okay? And this will start getting condensed over this particulate matter. So that provides the toxicity to the particulate matter. So they are carcinogenic in nature. This is how it looks in the SEM, okay? What are the options to control it? Engine-related modification, fuel quality improvement, and after exhaust. So I work on after exhaust treatment. So I'll explain you these three things in brief. There are three options. In diesel, another pollutant is NOx reduction. So you need to do the NOx reduction. For that, there is a technology called selective catalytic reduction, SCR. Okay, it's a bit of a chemistry. I'm just skipping this and I'm focusing more on the particulate matter. control, which is a bigger issue in fact, is that DOC and the DPF will look into these things details. These are the different after exhaust treatment options required, generally required. It depends on the strategy of automobile manufacturer, how do they control it, okay, engine out emission and after exhaust. Okay, it's fairly complex nowadays and fairly good amount of expertise are available now. This for the Euro 2, Euro 3, the Euro 4 and Euro 5, and we'll see for the Euro 6. First technology is diesel oxidation catalyst technology, DOC. This is the composition of your soot particle. Okay, here are hydrocarbons. Here is the ash, this carbon core. Unfortunately, with DOC, the catalyst cannot burn anything other than this hydrocarbon. So the particle is going and it is losing a part of this. Okay, only a part of this. So this is like a catalytic converter. You have a honeycomb. The exhaust is coming like this. The particles are coming like this, and the catalyst is oxidizing only these SOF, soluble organic fraction, we call it. And you still have a particle. Okay, so the efficiency of this device is low. It's about 20% or at the most 30%. The second device is diesel particulate filter. Okay, the diesel particulate filter, it's a concept that if you have a particle and you need to separate, what do you need? You need a filter. It's like preparing a cup of tea. You can keep it and try to decant it. Still the filtration efficiency will not be good. So what we do, हम लोग उसको छान लेते हैं, एक छन्नी लेके, एक filter लेके उसको quickly छान लेते हैं और coffee को छान लेते हैं. So if you have to separate the particle, which is either from the power plant or from the vehicle, especially from the vehicle, the most efficient device is filter. It is called diesel particulate filter, which is used for Euro 6. So now it is again the honeycomb structure, but the alternate channels are plugged. So the exhaust can come, enter and cannot go out. It has to travel through these walls of this honeycomb. Okay. So once it is traveling through these walls, these are like the membrane. These are like ceramic membrane. So these will trap or filter the particles and the clean exhaust is out. Okay. So very efficiently this particulate matter or the particles or the soot particles can be trapped. And very efficient filters are available in the market from since decade actually. Like Corning and NGK insulators and many other companies they are producing. And it's very easy to get up to 95% efficiency. So what is the problem? You can go to the market, buy a DPF, just fit it in your car, and your car is very clean. Okay, because it will filter that the soot and release the clean exhaust. The problem is after some time this will get clogged because of the soot deposition. Okay, it will start creating a back pressure, and at one point of time, of course, you will lose the engine efficiency, fuel efficiency, and the vehicle will be stopped. So cleaning of this soot is a major challenge. Okay, cleaning or management of cleaning or regeneration of this DPF is a major challenge because this soot burns at about 600 degrees Celsius, while your exhaust temperature, being a lean burn engine, your exhaust temperature is quite low. Okay, it's about 150 to 400 degrees Celsius at seldom. So you need to find some solutions. Okay, so DPF regeneration is a real challenge. Okay, so there are two ways. Active regeneration means you have to provide some heat. Okay, either you can have an electrical heater, which will be very expensive because the cost of energy penalty will be very, very high, or you can have a post-injection system where you are introducing fuel here, and the fuel will be burned just before the DPF. Okay, once you have enough soot accumulated and your back pressure is high. Okay, that is an indication you need to burn it. So there is a complex system for active regeneration. You can introduce a fuel, you can burn it, and it will provide a sudden rise in the temperature. Okay, and the soot will be burned and the filter will be cleaned. Okay, the challenge is it has to be controlled because if you shoot the temperature too much, it might shoot. Okay, because the particulate matter which got accumulated in the filter will also generate heat. Okay, so it has to be done carefully. Now the second option, which is known as a passive regeneration, okay, where a catalyst is used. So you've seen the DOC like this. You have the clear channels, okay, clear honeycomb channels. It's like a catalytic converter. What DOC does, you have a lot of NOx or NO, in the diesel exhaust. So this NO get oxidized into NO2, and this NO2 reaches the DPF, and the reactivity of NO2 is very, very high for the soot. So even at 250, 300 degrees Celsius, this NO2 can react with the soot which is trapped or accumulated in the filter and clean it. Okay, this is very, very common method. I have taken it from the Johnson method. Okay, this is called a continuously regenerating trap, and there are a lot of advancement in this. The issue with DPF will obviously the entire amount of exhaust, which is a very, very high volume, like 100 and 150 liters per second, needs to be filtered. Okay, needs to be flown through this DPF. So naturally, there will be a pressure drop. Okay, so although the efficiency of DPF is very, very good, very, very high, there will be pressure drop issues. So this is a trade-off. In DOC, the particulate collection efficiency is poor, pressure drop is almost negligible. In DPF, it is 95%, but the pressure drop is high. So there is a third technology called partial flow filter, which is more or less in between of DPF and like the DOC, where it's a different mechanism of collection of particles. Okay, we try to make a tortuous path so that it loses its momentum and get accumulated. Okay, but this is also not very commonly used, while it gives about 40 to 50% efficiency. And this is one device we would like to try for old vehicle, in fact. Okay, the regeneration process is almost same. Okay, so there are three very common technology: DOC, diesel oxidation catalyst; DPF, diesel particulate filter, very high efficiency; and in between, a partial flow filter. Okay, and there are commercial technologies available. So what are the R&D challenges and opportunity? Because I am a chemist and material scientist, so I look after the catalyst part, but we strongly collaborate, especially with the like Professor Avinash Agrawal from IIT Kanpur, and our own institutions like IIT Dehradun, and sometimes some foreign universities. Okay, so just I'll take 5 minutes and take you to the chemistry world. Okay, I told you the reaction. NO2 plus C is NO plus CO2. Okay, so you need to basically provide NO2 for catalyst. Most of the catalysts use a noble metal based catalyst. Okay, so the driving force for R&D is noble metal versus non-noble metal based catalyst. So worldwide there are limited resources of noble metal catalysts, which are platinum, palladium, rhodium. They are very costly. Okay, so if you can minimize the amount of these platinum, or if you can replace the platinum with other metals which are easily available in India, or we call it a transition metals, your job is done. So there's a great amount of research is going on worldwide. Okay, one is, as I told you, lower the amount of noble metal, or you replace it with the non-noble metals. All right. So we work on the low-cost catalyst. These are some chemistry terms like perovskite and mixed oxide based catalysts, which do not use, or they use a small amount of noble metal. These are the catalyst compositions. So I'm not going to go in the details, a bit of a chemistry, okay, where we look for the redox properties. Of course, we look for thermal stability and other parameters. Then we go for the three stage of catalyst evaluations. All right. First is a lab reactor, where we have a fixed bed, small laboratory reactor, or we can use a thermogravimetric machine to evaluate it. Second is a band scale facility using a small diesel engine, and third is the engine diameter test, which is a test. So I have already shown you this is another assembly, a very, very useful setup we have. We can create an exhaust composition. You can put your catalyst powder here, okay, and mix it with the soot, okay, and then flow the air and maintain the temperature. And after that, you can feed this to the gas chromatograph to check. And you can take a synthetic carbon, and carbon will burn and produce the CO2. So CO2 is plotted as a function of temperature. You can follow here. This is a CO2 plot, and CO2 coming from the soot oxidation. So generally, soot oxidation takes place at about 600 degrees Celsius. In this case, it is taking at about 374, the initiation. So the catalyst activity is pretty good, but still it is not possible to achieve 374 degrees Celsius by using diesel exhaust. So you need to have more, lower the temperature further. We have published a lot. If you are interested, you can go through these publications. The second level is evaluation of band scale evaluation, we call it. We prepare about 100 cc or 200 cc catalyst coated support. This facility I use at Kyushu University, Japan, where I have a lot of opportunity as a visiting professor. And we keep a diesel engine here, and a part of the diesel exhaust is passed through this, okay? And again, we can measure the CO2 and other emissions. Sometimes we need to also check for other emissions because what we call it a partial oxidation. Not necessarily it is producing CO2, sometimes it may lead to some other product, okay? Then for evaluation of prototype, we prepare a full-scale prototype using this ceramic honeycomb commercially available. There are very simple methods of coating it. This is how it looks like. This is a DOC we prepared with the one IIT Nagpur student, Pravesh, prepared, I think, with my student Rohini. He did some work in our lab. Then we need to do the canning of this, which can be easily done, and we can put some sensors for pressure and taking out the gas and also the temperature sensor. This is the engine dynamic setup you all know, so I'm not going to go into detail. It is coupled with the emission analyzer, okay, that EAPS, which is a particle size and number measurement, and the gas analyzers. This is the setup from Professor Avinash Agarwal's IIT Kanpur lab. One of the most impressive facilities I found in India because there are so many Indian dynamometers he alone maintained in his lab, and it's always available for all the good researchers who want to do some work. So thanks to him that we were able to analyze, evaluate our prototypes at the full scale. This is the result for CO emission, total hydrocarbon emissions, and like using both biodiesel as well as the commercial diesel. So again, I'm not going to go into details because of the short of time, but you can see that upstream and downstream, what is the difference in CO emission. This is upstream means without any catalyst or before the device. This is after the device, okay? So all the CO and SC emissions were also down, so as the particle number, okay? So we got a decent activity for DOC because in DOC you cannot expect more than this, okay? But even after prototype evaluations, it's a long way to go because we need to check the thermal, like the long-term stability. Then you need to work with the industry. They have their own a set of tests which is done, and then they have to also meet the Euro 6 or whatever norms we have to do that. This is now like in the Euro 6, it is getting very complex, and that's why I'm saying although after exhaust you can clean the exhaust, it's not a good idea to unnecessarily use the vehicles and emit the exhaust, okay, and then try to treat it, okay. It's not done. So this is fuel injection, then it will be DOC where you will burn the fuel, and it will be going to the DPF for active regeneration or the passive regeneration, okay. Then you will have a selective catalytic reduction of NOx. For that you need to introduce ammonia, okay, and somebody will explain you, of course, I'm sure. And then you need to also take care that there should not be excess ammonia. So this is ammonia slip catalyst. So it is fairly complex and expensive system, and that's why many automobile major are now preferring to lower down the production of diesel. Okay. So this is very impressive, the Euro 6. Okay, it's fantastic, and it was done in a planned way, and we should compliment both the government and automobile industry and all those who are involved that they were able to meet this deadline, although they had tough time according to me. Okay. So all these analysis were done before, 5 years ago, 6 years ago. This was like that time from 2015. If you do not introduce Euro 6 by 2030, okay, with the current standard, it will be a lowering up to 202, and then it will again start increasing. But if you introduce the world-class emission standard is the Euro 6, there's a likelihood that you can have a huge reduction in the emissions. Okay, really worldwide you can see wonderful emission. This is India. So in India, you can imagine this much of reduction is expected by implementing Euro 6. But there is a but here. Okay, this I have taken from Tim Johnson, whom I know is one of the very celebrated scientists from Corning, worked a lot in the auto exhaust. He explained that Euro 6 is fine because automobile industry, the emission control industry have taken care of it. But what about maintenance of the vehicle? What about how do you take care of these devices? Although there will be a foolproof system, there will be OBD systems and all these things. But for some reason, if there is a fuel adulteration or if there is a damage in the device or if vehicle is not maintained properly, okay, you can imagine that the Bharat 6 selective catalytic reduction system is disabled for something. Sometimes Some people, they just remove the system, okay? The NOx emission can go up by 10 to 15 times. And light duty vehicle, if you remove the catalyst or catalytic converter or catalyst device, the emission could be as high as 40 times, okay? So if 10 or 20% of your vehicles are not using or for some reason the devices got damaged, you may not be able to get benefits out of this vehicle. And what does it mean? You have a huge investment. On the fuel itself, I think there was a 60,000 or 70,000 crore were invested to get the Euro 6 fuel, and every car will have about 50,000 investment on average, I believe, for these kind of devices. So all this will not sort of get utilized, or it will be a waste of money if you do not maintain the vehicle. Okay, so for new vehicle, it is very standardized because automobile industry has to meet it. They have to go for the type approval test. Okay, it is done very nicely. They have to go for COP, okay, test. But for in-use vehicle, okay, we have pretty poor, I would say, system in India. Okay, so vehicle manufacturer's responsibility is straightforward. Okay, they always very sincere. In fact, type approval or COP, conformity of production. Vehicle users' responsibility to comply with the ideal emission norm (PUC), which is I think in a bad shape so far. To comply with the fuel requirement, that is okay, done. To comply with IRDAM program, if any, we do not have a proper inspection and maintenance program or inspection or certification program. So now it should be done very strictly in a systematic way, because all the developed world has got a very good INC program. Okay, sometimes their certification, annual certification costs so much that it is more expensive than buying a second-hand car. But in the second-hand car, you will not get that certificate. Okay. So now there is a wonderful development, but it should happen fast. Okay, there are test centers being set up, not like POC, but for this INC center. Let us hope. I just skipped those slides because of because of the want of time. Okay, the last 5 minutes I'll spend on the retrofitment, which is very important. Why it is required? Okay, you know, in India the vehicle life is very high. Okay, and I have already explained you there is a substantial amount of carbon footprint and energy footprint during the production of the car. So it's not a good idea you throw the car after 5 years, what is happening in the developed world. Okay, so if possible, if your engine technology permits, you should try to maintain the car and possibly try to retrofit in terms of emissions and use it. Okay, for that you should target the most polluting vehicle, okay, which are giving the high emissions. Targeting most used vehicle like taxis, heavy duty truck which run day and night. Targeting vehicles with maximum impact. For example, city bus and intercity bus. So intercity bus is out of city for a while, but the city bus is all the time inside the city. So if your city bus is really dirty or emitting, it will have more impact. Okay. Then there are implementation challenges. So this is your vehicle population. Okay. So as of now, probably you have got about 25 crore vehicles in India, more than that, about 26 crore vehicles. Okay, out of which you can count how many vehicles are Euro 6 vehicle, because it is just introduced this year from April 1st. And you can also count how many are Euro 4 vehicle. So this is to make you realize that majority of your vehicle is an old population. So although you have a very clean population now, okay, very clean vehicle now, its contribution to overall vehicle population is very small. So these old vehicles will keep on emitting the high emissions. We cannot throw them for economic reason, and also for the reason that there is some embedded energy. We already invested in that. So is there any possibility we can retrofit these vehicles with these devices like catalytic converter, diesel particulate filter, and make it clean for next 5 years? And then of course we need to throw them. So that is called retrofitment. So we did a project 10 years back. That time it was done with the PMT, Pune Municipal Transport Company. We used these buses, which were Euro 1 buses mostly, in fact Euro 0 and Euro 1 buses. And those were obviously pretty dirty buses, because that time the emission norms were not very good. And those were emitting very high. So we checked the exhaust temperature. The problem with these city buses is they fly throughout the day inside the city, naturally. So the exhaust temperature is very low. So we checked with this project we did with the Johnson Matthey and Cummins. So they checked the exhaust temperature, which was not suitable for these devices. Okay. Then we did some kind of an insulation and other things. Okay. We tried to find out that which buses are okay to use it. and then we retrofitted with the DOC and partial flow filter. Okay, and these are the devices which check the back pressure, and then it can trigger either bypassing the exhaust or regenerating the exhaust. It's not easy to use the city buses because the passengers are there, so we need to do all the care. We need to take all the care. And it's for the first time we used around 2009, probably way back. Okay, first time we used onboard testing of vehicle on the actual road. Okay, so we simulated the passenger by putting the stand bags here, and we checked the PM emissions before the device and after the device. But the soot load was so high that these devices used to get clogged very easily, and we used to open it, physically clean it, and in fact sometimes we found the devices were damaged. Okay, because there will be soot accumulation, and when the soot will be burned, the localized temperature will be very high. Okay, look, high is more than 1000 degrees Celsius. So we concluded that probably the Euro 1 buses were not suitable for retrofitment because those were like mechanical engines, obviously up to Euro 2, Euro 3 probably. Okay, very high soot was there. It is not good. But we recommended that time in future probably retrofitment will be a good idea, like Euro 3 and Euro 4. Okay, after certain AG could be good candidates for retrofitment. It's pretty complex in nature. Okay, so now we proposed a pilot study which has been approved, and now we are working with ADIT. Okay, they are our partner, as well as ECMA and some of the oil company. The actual testing will be starting from the next month. Okay, the vehicle have been selected, some devices have been selected. Okay, so I'm very much looking forward for those results, and next time we should be able to share with you those things. What are the NEERI's recommendation? We believe in 3R or R3: repair, retrofit, and only then you should replace. Okay, so in-use emission compliance, very straightforward, wonderfully done. But sorry, the automobile industry-related compliance, okay, the type approval and COP are very nicely done. But in use by the vehicle owner, we need to do the faster implementation of IMC centers. Okay, we need to possibly involve all these vehicle manufacturers because their service station can serve very good centers. In fact, PUC needs revamping completely. There are new technologies like remote sensing, GPS-based sensing, OBD sensing. We should use that. More reliable data required for emission control devices. What is happening after 5 years, 4 years? Nobody knows. Sometimes you go to workshop, they say, sir, isko nikal dijiye, fake detail. Sometimes they say कि मैं उसको heat कर देता हूँ, sometimes they say कि मैं उसको clean कर देता हूँ. All this should not happen. We should repair, we should retrofit, okay, in the proper vehicle, and then there is no possibility, then we should replace. But as I mentioned you, we need to look into the broader issues where we need to reduce the requirement of travel, first of all, okay, that is very, very important. So we need to work on the emission control from the in-use vehicle, okay? So mainly we need to really work on that. So I'm just repeating this slide because this is a very important message. Reduce vehicle kilometer, plan your cities like that, okay? Reduce fuel per vehicle kilometer, plan mass transportation. It's good development about the matter and all these things. Efficiency is taken care by the automobile manufacturers. Reduce pollution control, so new technologies are coming up. Reduce fuel cost, okay? So control of emissions only from the new vehicle is not important. We need to also consider the old vehicle. Only then we'll get the overall benefits. So this is the summary. I'm just closing now and repeating the energy demand is rapidly increasing. Fossil fuel will be used for decades to come. Several energy options will be required. So is the improved energy efficiency. Carbon capture will be important, CCUS. Life cycle assessment is very important in Indian context. Efficiency will be one of the key. It's my buzzword actually. Okay, we need to do the policy issues and holistic approach in fact. Okay, and there's a good R&D opportunities for all of us. Don't take it as a negative slide, but I sometimes show this. Gus Patel is a big name in environmental because he was the boss of World Resources Institute. What he says, I used to think the top environmental problem we have today heard about the GHG problem, global warming and the climate change, and the automobile emissions problem. So he says, I used to think the top environmental problems were biodiversity loss, ecosystem collapse, and climate change. I thought that with 30 years of good science, we could address those problems, but I was wrong. The top environmental problems are selfishness, greed, and apathy. And to deal with those, we need a spiritual and cultural transformation. And we scientists do not know how to do that. That means we need to really control our greed, okay, improve our resource efficiency. We should never waste anything, okay, only then we would be able to achieve what we want. So with this, I would like to thank you very much. I've taken a little bit of more time. I'm sorry for that. And I hope you could follow it and find something useful. Thank you so much for Professor Ronak Shah, okay, and I truly appreciate his efforts to organize such a wonderful course, okay, and thanks to my students, colleagues, and collaborators. So I'll stop here, and if you have any questions or discussion, we can quickly take up. Otherwise, write to me, and I'll respond to you also later on.
Sir, first question, can you recommend a good LCA software, life cycle assessment software?
I'm forgetting the name, but yes, which one we are using? Just give me a sec, and by the time we can go for next question, and I'll get back to you.
In India, is carbon footprint calculated based on greenhouse gas protocol? It is developed by WRI and World Business Council. If not, then what standard is followed?
These are the two standards. Of course, we can do that, okay, but it's not so easy to follow that. So as I'm telling you, it is contextual, okay. It's always a contextual, okay. So what we are using, a couple of group at IIP and NEERI, they are combining these two things, you know, like the LCA plus carbon footprint, because through LCA you need all the process and steps which is consuming energy, okay, and for every step then there is a calculator, okay, where we are, it's very important to find out. I gave you one example, transportation of coal. So transportation of coal in terms of the environmental footprint is not a big deal in many countries because they do it very systematically, okay? While in India, it is very important, okay? Just give me a sec. In fact, I need to.
Thank you, sir. Another question, in DCR, what is the NH3 life, ammonia life?
Please say again.
In DCR, what is the NH3 life?
I think there's some confusion now. Are you asking for the selective catalytic reduction, SCR? Okay.
DCR.
What is that?
Dr. Manish Kumar Mistry, he asked this question.
Just a minute. I'll.
Sorry, it is SCR.
Yeah. Okay. Okay. First of all, somebody asked me about the this LC softwares. I just recollected. Grabby we are using. Okay. The Grabby is one of the best. I suppose we have a licensed version, and we are collaborating with 2 or 3 institutions. If you are interested, I'll connect you to the right people. Where and they are trying to, in fact, to contribute now, which I also feel very strongly to contribute under the Indian context. Okay. About the SCR, yeah. What was the question that? Just a minute, I'll read.
SCR, in SCR, what is the NH3 life?
NH3 life.
Life.
You know, NH3 is a kind of a reducing agent where just fundamentally you can understand that in case of a carbon monoxide and the hydrocarbon, we need a oxidation reaction because CO and SC needs to be oxidized to CO2. While in case of a NOx, you cannot oxidize NOx because it's already oxidized. So you need to reduce it. So you need a strong reducing agent, which is ammonia. So ammonia is provided in a tank, okay, which is either ammonia or the urea, okay, like the, and then it is a kind of a precursor to the reactant, okay, where it is using as a reducing agent. So there is no question of a life, but the only problem is whatever ammonia you are introducing, you may not be able to use it completely, okay, or it is not required. So there will be an excess ammonia which may come out of exhaust, okay. which is not good. So there is an ammonia slip catalyst. Okay, so ammonia is caprolly used for the reduction reaction.
Okay, sir. Thank you.
Okay, thanks for the.
Good afternoon, everyone. I, on behalf of Mechanical Engineering Department, ADIT, would like to express our sincere thanks to Dr. Nitin Labhasetwar for accepting our invitation and gracing us with his important work and sharing his findings on clean energy, emission control, retrofitment, and replacement of components. Thank you, sir, for accepting our invitation, and we look forward to hear from you in the future also. Thank you, sir.
Thank you very much for this opportunity to share some of our research work. And I would like to again compliment and thanks to all the participants for your kind attention and time.
One announcement for the participants. It is requested that all the participants must turn off their videos and they must be muted in the last session of today.